Somewhere in a weather journal kept by a farmer in Vermont, there is an entry dated June 6th, 1816. It reads simply, "Snow today, heavy frost last night, crops are dead." It was June. That entry alone might be dismissed as a quirk of New England weather, a freak cold snap, an early season anomaly, but the same record appears in different handwriting from Connecticut to Pennsylvania, from France to Germany, to the highlands of China, from the rice paddies of India to the wheat fields of Switzerland. The same June, the same cold, the same dying crops, the same desperate silence where a harvest should have been. Something happened in 1816 that the world was not prepared for, and the closer you look at the historical record, the diaries, the government registers, the price ledgers, the mortality tables, the harder it becomes to fully explain why it was so catastrophic, and why so few people today have ever heard of it. This is the story of the year without the summer. To understand what happened in 1816, you have to go back 1 year earlier, to April 5th, 1815, to a mountain on the Indonesian island of Sumbawa. That mountain was called Tambora. At approximately 7 o'clock in the evening, Tambora erupted in what would become the single most powerful volcanic vent in recorded human history. The explosion was heard over 2,500 kilometers away, in parts of modern-day Malaysia and on the island of Sumatra. Ships in the Java Sea reported ash falls so thick, their crews believed that they were under cannon fire from an invisible enemy. The mountain itself, which had stood at an estimated 4,300 meters before the eruption, was reduced to roughly 2,850 meters. 12 cubic miles of rock and ash were hurled into the atmosphere. 71,000 people on the island of Sumbawa died within days, some from the pyroclastic flows, some from the tsunamis, most from the darkness, the ash, and the starvation that followed. But what happened on that island was only the beginning. The real consequences of Tambora would not be felt on Sumbawa. They would be felt 10,000 miles away, a full year later, in places that had never heard the name Tambora and never would. The year 1816 began quietly enough in Europe and North America. The Napoleonic Wars had ended. 1815 had been a year of upheaval, but also of hope. People were exhausted from 2 decades of war. They were ready to rebuild. They did not know that something invisible was already in the sky above them. Here is where the story becomes unusual. Tambora erupted in April of 1815, but the climate effects were not felt fully until 1816, and when they arrived everywhere at once in ways that confounded scientists and governments for decades. In April of 1816, temperatures across the northeastern United States were normal, perhaps slightly cool, but unremarkable. Then May arrived and did not warm. June came with frost. In New England, snow fell on June 6th, June 7th and June 8th, and did not fully melt until late in the month. July brought a brief thaw, enough to give false hope. Then August, the height of summer, delivered another killing frost that destroyed what little had managed to grow. The records from this period are extraordinarily precise, and that precision makes the pattern even stranger. Thomas Jefferson, then 73 years old and farming at Monticello in Virginia, kept detailed weather records throughout his life. His journal for the summer of 1816 notes temperatures that never reached the levels required for a successful corn harvest. He wrote to a friend that the season was unparalleled in the memory of any person living. Jefferson was not a man given to exaggeration. He was a man of measurements and data, and his measurements told him something was deeply, fundamentally wrong. In Europe, the anomaly was equally severe, but with a peculiar asymmetry that historians still find difficult to fully account for. Switzerland recorded 18 months of almost continuous rain. The summer mean temperature in Western Europe dropped by an estimated 3 degrees Celsius, below the long-term average. 3 degrees sounds like very little, but 3 degrees, sustained across an entire growing season, is enough to collapse an agricultural society. And yet, not every region suffered equally. Eastern Russia reported a relatively normal summer. Parts of the American South escaped the worst of the cold. The pattern of disruption was, in a word, irregular, and irregular patterns in climate, patterns that do not follow the predictable logic of a single atmospheric event, are precisely the kind of patterns that, once you start looking, refuse to resolve into a simple explanation. The year 1816 produced one of the most dramatic food crises in the Western world since the Black Death. In Switzerland, the grain harvest failed entirely. Bread prices rose by over 300% in the space of a single year. The Swiss government, such as it was at the time, had no mechanism to respond to a famine. Of this scale, people ate nettles, they ate the bark of trees. Contemporary accounts from the canton of Bern describe families who slaughtered their cattle in summer because there was no feed for them and then had nothing to eat by winter. In France, the failed harvest of 1816 reignited political instability that had barely subsided after Napoleon's fall. Bread riots occurred across the country. In the German states, an estimated 200,000 people died of famine-related causes. In Ireland, the cold and wet summer destroyed the potato crop. A grim rehearsal, some historians have noted, for what would happen again 30 years later. The mortality records from this period present a pattern that is troubling to read. Parish death registers across England, France, and the German states show spikes in mortality, beginning in the winter of 1816 and continuing into 1817 and 1818. But what is strange about these spikes is not merely their size, it is their composition. The deaths were not concentrated among the very old or the very young. As famine deaths usually are, a significant proportion of the victims were adults between the ages of 20 and 40. The people who should have been the most resilient. Some historians argue this reflects a secondary epidemic of typhus, which followed in the wake of the famine. Others point to the enormous displacement of populations as a factor. In parts of Germany and Switzerland, entire communities abandoned their villages and moved westward, toward the Rhine, toward France, toward the coasts, looking for food and land. This movement of people, rarely discussed in mainstream histories, left traces in municipal records, church registers, and most unusually, in a set of files held in the Swiss Federal Archives that were not fully examined by researchers until the late 20th century. The official explanation for the year without a summer is as well established in climate science, and it is, in its broad outlines, almost certainly correct. The eruption of Tambora injected an estimated 150 to 200 million tons of sulfur dioxide into the stratosphere. This sulfur dioxide combined with water vapor to form sulfate aerosols, tiny reflective particles that dispersed across the globe over the course of 12 to 18 months. These aerosols reduced the amount of solar radiation reaching the Earth's surface, cooling temperatures worldwide. The mechanism is understood. The physics are sound. The connection between Tambora and 1816 is supported by ice core evidence, tree-ring data, and contemporary atmospheric observations. But the official explanation, thorough as it is, leaves several questions unanswered. The first is the question of precedent. Tambora was not the first massive volcanic eruption in human history. The eruption of Laiki in Iceland in 1783 was catastrophic. The eruption of an unknown volcano in 1257, now believed to have been Samalas, also in Indonesia, may have been even larger than Tambora. And yet neither of those events produced a climate disruption quite as severe or quite as geographically concentrated as what happened in 1816. Some climate scientists have suggested that Tambora did not act alone. There is evidence in ice cores from Greenland and Antarctica of a series of smaller volcanic eruptions in the years immediately preceding 1815, eruptions that may have already begun to cool the climate before Tambora delivered the final blow. This theory, sometimes called the volcanic forcing cascade, would explain why 1816 was so extreme. Tambora was not an isolated event. It was the last push in a sequence that had been building for years. The second unresolved question is about the sun. In 1816, the world was in the depths of what astronomers now call the Dalton minimum, a period of reduced solar activity that lasted from approximately 1790 to 1830. Sunspot counts, which correlate with the sun's energy output, were at their lowest recorded levels during this period. Some researchers have argued that the combination of reduced solar activity and a major volcanic eruption created a compounding effect that no single factor alone could have produced. This is still debated. The contribution of the Dalton minimum to the cold of 1816 is a question without a settled answer, and in the gap of that unsettled question, other interpretations have occasionally taken root. There are records from 1816 that historians rarely quote in full. In the archives of the Royal Society in London, there is a collection of letters sent to the Society's secretary in 1816 from observers around Britain. Many of these letters describe atmospheric phenomena that the writers clearly found: alarming, unusual sunsets of deep red and orange, a persistent haze that gave the sun a pale, diminished quality, even on clear days, and a silence in the countryside that several correspondents attributed to the absence of insects and migrating birds. One letter from an observer in Norfolk, dated August 1816, describes the sky on a clear evening as the color of old blood. The writer was a physician and described himself as a careful observer of nature. He had been keeping weather records for 20 years. He wrote that he had never seen such skies before and that his neighbors attributed them to a coming pestilence. They were not entirely wrong. The haze the Norfolk physician observed was real. It was the sulfate veil of Tambora, still spreading through the upper atmosphere more than a year after the eruption. And the pestilence, the typhus, the dysentery, the famine fevers, was already on its way. In the American state records, there are entries from city councils in Boston, New York, and Philadelphia from the summer of 1816 that record emergency measures for the relief of the poor. These records are brief and bureaucratic, but read together they tell a story of urban populations under severe strain. The price of oats in New York doubled between April and August of 1816. The price of corn tripled. Newspaper accounts from Philadelphia describe long lines at charity kitchens and an unusual number of families selling household furniture in the streets. In the Swiss Federal Archives, there is a document that was catalogued in 1974, but received little scholarly attention until a paper published in 2019. It is a record of a survey conducted by cantonal authorities in 1817, asking village administrators to describe the conditions in their communities. The responses are harrowing in their plainness. One administrator writes that 3/4 of the families in his village had consumed their seed grain by February. Another notes that several families had left their homes the previous autumn and had not returned. A third reports that the village priest had buried 23 people in a single month, a number, he writes, that equals all the deaths in the preceding 4 years. Combined, these documents were not hidden. They were simply unread. They sat in folders in basements, filed under administrative categories that did not advertise their content. They were the paperwork of catastrophe. Mary Godwin was 18 years old in the summer of 1816. She was staying at the Villa Diodati on the shore of Lake Geneva in Switzerland with her future husband, Percy Bysshe Shelley, and the poet Lord Byron. The summer was supposed to be a holiday. It became a captivity. The cold and the rain were relentless. The group could not go outside for days at a time. The light was strange, the dim filtered light of the sulfate veil, which made every afternoon feel like a late autumn dusk. Byron described the summer in a poem he wrote that year, which included the lines, "The bright sun was extinguished, and the stars did wander, darkling in the eternal space." He called the poem Darkness. It was not a metaphor, it was a description. On one of the cold, rainy evenings at the Villa, Byron proposed a ghost story competition. The group told stories by candlelight. Mary Godwin, who would soon become Mary Shelley, began a story about a scientist who created life from dead matter. That story became Frankenstein. Published in 1818, the novel is typically discussed as a work of imagination and philosophy. It is less often discussed as a document produced by a group of people trapped indoors by a climate catastrophe, in a country where children were dying of famine. Across the Atlantic, a farmer named Seth Hubble in Vermont kept a diary through the summer of 1816. His entries are among the most detailed surviving accounts of what ordinary people experienced that year. He wrote about replanting crops 3 times after successive frosts. He wrote about borrowing seed from neighbors who had little to spare. He wrote about watching a hailstorm in July destroy the small amount of corn that had survived the June frost. He wrote in an entry from September that he did not know how his family would survive the winter. They did survive, but many did not. Vermont lost a significant portion of its population in the decade following 1816, not entirely from death, but from emigration. Families packed their belongings and moved west, into New York, Ohio, Indiana. The phrase historians use for this migration is the fever. People caught the fever to leave, to start over somewhere warmer, somewhere more reliable. The migration changed the settlement pattern of the American Midwest permanently. Towns that would not have existed, or would have been settled a generation later, were built in Ohio and Indiana in the 1820s, partly because people fleeing the unreliable soils of New England needed somewhere to go. A single volcanic eruption in Indonesia had rearranged the population of a continent. There are still questions embedded in the story of 1816 that resist clean answers. We know what Tambora did to the atmosphere. We understand the mechanism, and yet, the specificity of the damage. Why Vermont suffered more than Virginia? Why Switzerland suffered more than Russia? Why the summer was cold, but the winters were not always colder than normal? Those irregularities have never been fully resolved. Climate is a system of systems, and the interactions between a volcanic eruption, a quiet sun, a recovering ocean, and an atmosphere still carrying the chemical memory of previous eruptions are interactions that even the most sophisticated models have not fully replicated. What we are left with is this. The world of 1814 and the world of 1820 were not the same world. The food systems were different. The populations had moved. The political instabilities that erupted in Europe in the 1820s and 1830s had roots that ran back through the hungry years, to the cold summer when Mary Shelley wrote about the creation of unnatural life, and Seth Hubble watched his corn die for the third time. There is something unsettling about how quickly it happened, and how quietly it has been forgotten. The people who lived through 1816 knew something had changed. They could see it in the wrong-colored sky. They could feel it in the June frost on their hands. They wrote it down in parish registers and government surveys and diaries that sat in basements for 150 years. Some of them, like Byron, found strange beauty in the darkness. Most of them simply endured it, or did not. The question worth sitting with is not really about volcanoes or sulfate aerosols or solar minimums. Those are the what and the how. The question is about how thin the margin is between a functioning civilization and a failing one. In 1816, that margin was measured in degrees of temperature. 3 degrees of cooling, a failed summer, a bad harvest, a ripple that became a wave, that became a flood. What might one bad year look like today? Maybe the story of 1816 is simply a historical curiosity, a dramatic episode from a more fragile age, before modern supply chains and global food systems and climate science. Or maybe the people who survived it understood something we have since allowed ourselves to forget. That the sky can change without warning, that the harvest is never guaranteed, and that the distance between a good year and a year without summer is smaller than anyone wants to believe.